Let's look at another application of exponential functions. And in this case, we're going to look at radioactive decay, which, if you picture on a graph, you begin with some amount of a radioactive material, and over time, the amount dissipates. It decays. So we'll have some initial amount up here, and then over time, the radioactive material decays and eventually gets closer and closer and closer to this asymptote of 0. So how do we represent radioactive decay with a model or an equation? There's a couple ways to do it. We're going to look at the model that says the amount of radioactive material A is equal to the initial amount of radioactive material A naught, that's A with a subscript of 0, times 2 to the power of negative T over H, which is the half-life of the radioactive material. So let's write out what each of these pieces is. A is the amount of radioactive material after time t. And so A and T are the variables here. So A and T are the variables. If the time changes, the amount of radioactive material changes. If the amount of radioactive material changes, then time has to have elapsed. So these are the variables in this model. Then we've got A naught, which with the subscript of 0 usually means like a starting amount. So in fact, it is the initial amount of radioactive material. And H is the half-life of the radioactive material. These are both constants. They don't change. Okay. Now what is half-life? Half-life is a time value, and it's the time it takes for the amount to decay by 1/2. It's the time it takes for the amount to decay by 1/2. So if we look at our graph now, we can see that the starting amount here is A naught, whatever value this is on the y-axis, if you will. And T is, what's being measured on the horizontal axis, and A is what's being measured on the vertical axis. What we can't see over here is H. Not directly anyway. H is, all right, if I've got A naught, how long does it take for A naught to be cut in half? And we can map it over here, and we can see that this amount of time here is the half-life. So every time that amount of time elapses, the amount should cut in half again. So half-life is the amount of time it takes for the amount to decay by 1/2. Sometimes we know the half-life, sometimes we do not. We'll do one example here. The way models always work is being able to read a problem and interpret what it's saying. So let's say it takes 20 days for a radioactive, it takes 20 days for a radioactive substance to decay by, let's say, 15%. Okay? What is, let's make this a two-part question. Part A, what is its half-life? And I like to visualize this on a graph. It takes 20 days for a radioactive substance to decay by 15%. So here's the idea. It doesn't matter what we start with, but it decays by 15% in 20 days. So let's say that the vertical axis, the amount of radioactive material, is measured in percent of the substance. Okay? Well, let's say that we're going to start with 100%. And our time is measured in days, so this would be 0. And we know after 20 days, it decays by 15%. So in other words, after 20 days, there's still 85% remaining. So our graph does this kind of thing. And keeps going like this. The question is, what is the half-life? Well, if we look at our model, A equals A naught times 2 to the negative T over H. If we want to know the half-life, then we have to plug in values for A naught, and T. We can't have two unknowns. So if H is our unknown, the other three values need to be known. And we can see that the amount and the time are tied together. So if I look at this point on my graph, I know that when T is 20, the amount is 85. Okay? And so I've got A and T, I need A naught. Well, we can see A naught, the initial amount is 100. So all we do is we plug those values in. 100 equals, sorry, not 100. A is 85. 85 equals 100 times 2 to the negative 20 over the half-life H. And now the only variable we have is H, so we can do some algebra to solve this exponential equation. It's exponential because the variable H is in the exponent. So we'll divide both sides by 100. 85 divided by 100, I could just leave as a fraction. I could reduce it. I could write it as a decimal. I like writing it as a fraction because I don't need to worry about reducing it to solve for H. That equals 2 to the negative 20 over H. Now I need to get rid of the base of 2, so I'm going to take a log base 2 of both sides. And on the right side, the log base 2 cancels with the exponential of base 2. So I can see log base 2 of 85 over 100 equals the fraction negative 20 over H. So now I need to get H by itself. And since I've got a fraction, I'm going to multiply both sides by the H. So the right side turns into negative 20. The left side is H times log base 2 of 85 over 100. And now to get H by itself, I'll just divide by the log base 2 of 85 over 100. If you can't do a log base 2 on your calculator, you have to use the change of base formula. So you'd have to use the natural log button, and you would do the natural log of 85 over 100 over the natural log of 2, and make sure you divide by this entire fraction. And in either case, whichever way you type it, you should get about 85.3. And the unit on the half-life, because it's a time value, is days. Okay, so the half-life of this radioactive substance is 85.3 days, meaning after 85.3 days, we should drop from 100% down to half of that at 50%. All right, let's do part B. Now that we know the half-life, we could ask, what model represents the amount of material left after t days. Well, remember a naught and h are constants, and a and t are variables. So a equals a naught, which is a constant, so we started with 100%, times 2 to the negative t, t is a variable, over h, which is, now we know, a constant, 85.3. And now we know that, and by the way, A would be the percentage, so we could say where A is the percent of the substance remaining. The percent of the substance remaining after T days. So now, if I wanted to answer other questions with this model, I could perhaps ask how much of the material remains after 10 days. And I could simply plug a 10 in for T and calculate. Or I could say, how many days does it take to decay to 20%? Well, I'd plug in 20% for my amount and solve the equation using algebra for T to get the time. And that is how you solve radioactive decay problems with this particular model. And in general with models, read the problem, understand what the model is, and plug the values in appropriately. Knowing what the variables and constants are can be very important.